Okay, enough people have joined. Mark, I think you can go ahead and get started with your session.
Okay, then. Thank you a lot for joining. Today I'm gonna give you a quick introduction into deep learning and neural networks. And we're also gonna build a simple neural networks ourselves. So to be able to do this, I would encourage everyone here to be able to have access to Google Colab on their computer. So if you're joining with your phone or iPad, you probably cannot participate in 3/4 of this session now. But yeah, the first half will be some theory, so we actually know what's going to happen in this session, and then afterwards going to get more practical. And deep learning is basically a subset of machine learning. For everyone who doesn't know it, basically machine learning with neural networks. So what we do is we model the neurons of our brain artificially in specific well, mathematical functions, and then we update the weights to have a learning process. The core concept is very, very simple. You have an input, you perform matrix multiplication on this numeric input with parameters, and then you compare your output you get to the ideal output you want to get, and then update your parameters so they fit the data you have better than what you have already. So the most basic example of a machine learning problem would be linear regression. You have a linear function and you would change the parameters so that it models the data as closely as possible. This is not a very complex problem, so you don't need any neural networks for this, but when it gets more complex, neural networks are the way to go, and they can, well, have incredible prediction power on modern problems, as you probably all know with language as well. The core function, and this is not that important, but I'm still going to cover it. The core function here is that you have weights and biases. So W are the weights and B are the biases. Those are changeable parameters. Those are updated. And your input X is then, well, changed with these factors and additions, so you get your output. And this is the simplest form of a perceptron, so a single neuron layer you could get with two input numbers and an output number. If you arrange them in more complex combinations, you get this neural network. And this is how most modern machine learning problems and AI models are handled today. So in this case here, we have three parameters, two weights and one bias. And in most normal neural networks, like in large language models, for example, with ChatGPT, we have billions of parameters, and a 7 billion parameter model is considered very, very small. So that means lots of weights and parameters to fine tune, lots of computing. So that's also the reason that GPUs are so expensive now. And this formula is not, it's basically the same here, but if you have more inputs, obviously you add them all together then. Okay, the way you update those weights is in a process called the gradient method. And this works by first predicting the output with the current parameters you have, then calculating your loss, so the actual difference between what you calculated and what should be there, so the ideal output. And then you take a look at which neurons or parameters caused that error, caused your model to make a mistake, and then update them in the right direction so the error is minimized. You can think of this like a 3D landscape here. Obviously, in reality, it has many more dimensions, but what you essentially try to do is find the minimum in this loss landscape. So where the loss, your error, is the least. And then the way you do this mathematically is you, well, differentiate the loss function, then try to find the gradient and always take steps closer to the minimum here. In our case, or the problem we want to solve is a classification problem. So we have image data as an input. Every pixel has numeric information, in this case RGB information, but we're going to only worry about grayscale images, so it's less data to compute. And in the output neurons, so the last layer here is then for every class we want to predict. In our case, that's well, in this PowerPoint it's animals, but in the model we're going to build today, that's clothing pieces. And each neuron has then a number that gets computed in the output neurons, and the highest number essentially would be the correct, would be the label the neural network predicts here. So you convert the raw logits normally into probability distributions and then into the predictions that your model outputs. There are a lot of different architectures of neural networks. So I just covered here the most basic linear neural network, and that's also one we're going to build today. But generally for image classification problems and generally for image-related problems, you would normally use a convolutional neural network that also has specific filter layers, which will extract information from the image before you have those normal neuron layers afterwards. And then there are also a bunch of other noteworthy architectures. The probably most interesting one here is the transformer, which is the underlying architecture behind large language models like ChatGPT or Claude. So yeah, this is also very interesting. Okay, this is a personal project I was doing, but I won't cover it today because we don't have that much time, since the neural network process is quite complex. So with that theory out of the way, let's get started with practical stuff. And for that, everyone should be at their PC. I want you to open Google Colab. So colab.research@google.com, and then create a notebook. And then you should see this here. Once I'm going to wait a couple minutes and then we'll continue from here so that everyone is, well, pretty set up. Let's title this then it's Google Colab. I'm going to share the link in the chat then if that causes trouble. Okay. Hopefully everyone should be at Google Colab right now, and you need to create a new notebook. So, well, for files, create a new notebook, and then can you request the materials will be available? Well, the materials are available. You just need to open Colab on your notebook, and then you should get started. You don't even need to pay for Colab Pro. Okay, this works on the free plan as well. So is everyone at Google Colab right now? Because if not, then well, we have to wait a bit. This is basically Google's research platform, and that gives you access to cloud servers, so you can perform machine learning work on your device, but get access to GPUs and other processing units. And that way you also don't have to set up manually on your device. Okay, if anyone still has problems with opening Colab and creating a new notebook, please put it in chat. If not, I'm going to assume that everyone is at that point now, and we're going to continue. So this will take a while to connect, not a while, but a bit. You can see your resources on the sidebar here. And once you run your first cell, in this case, NVIDIA I'm running this NVIDIA SMI, which normally gives you information from the GPU you're running it. Right now, the command's not found because I'm not running it on the GPU, but on the CPU, which is also sufficient for this simple problem we're tackling. But once models get more complex, you need the faster computing time, of course. Okay, so let's get started with the coding then. The first thing you always do in every machine learning problem is download the data and familiarize yourself with the data set. Okay. So what we're going to do is we're going to download an open source data set of clothing images. That's called Fashionist. They are grayscaled, and they are already labeled with the classes they belong to. So for example, t-shirts or pants. And our model's task is then to take this image as an input and say which clothing piece is depicted on it. And to do that, we're going to import, well, PyTorch libraries. And for anyone who doesn't know any machine learning processes yet, PyTorch is the standard library used for machine learning works. It has lots of frameworks for programming in it, and it's very helpful if you want to perform new network programming here. So in this case, we'll need from the PyTorch vision library the data sets. And if anyone has trouble, please say it in the chat. So the way you do this is you click on code, then you input the code. I'm structuring it also with text here, but should be very straightforward. It's working on my phone for now. Well, you can try. It might work there, but let's see. It should be easier on your PC, so I encourage everyone to join from the PC. Okay. And we also need some transforms, because raw images are not used for our machine learning tasks. Okay. Generally, you need numeric data. So we first need to convert our image data into numeric data. And in PyTorch, you work with numeric data in form of tensors. You can think of tensors basically like matrices with multiple dimensions. And in our case, they would be matrices with one color channel dimension, and then width and height. So every pixel would be a number in this matrix. And yeah, that way we could process that. Okay, to download our datasets, we're going to need two datasets, a training set and a testing set, because obviously we don't want to evaluate a model on the same data we trained it on. Otherwise it would, just only learn from this data and then not generalize well. So that's also best practice. And the dataset is called Fashionist. It's already provided in the Torch Vision library. Otherwise, you would have needed to download it yourself, for example, from Kaggle. I'm going to create a directory called data, so a folder called data where this dataset is downloaded into. In this example, we need the training data, and we want it in forms of tensors, so 2 tensors. And this is already grayscaled here because I already coded this once to test if everything works, and now Colab remembers what I inputted last time and already auto-completes most of it for me, but yeah. Okay. No transforms. Transforms are sometimes used if you need more variety in your data. So, for example, you can rotate your images, but we don't need this for now. And then we'll also download our testing data set. Here, we're not using the training set, of course, so make sure your train is put to false. And then download true to tensor. No target transforms. Okay. If everyone is at this point, you can press Shift and Enter. Yes, forgot coming here. Okay. And then it should download the dataset and run this cell. Okay. Now the data should be downloaded. If you want to look at how many images are in this dataset, you can get the length like this. So the length of the training data. And let's also get the length of the test data. So we have 60,000 images in our training set and 10,000 in our testing set, which is a usual split. Normally you have like an 80-20 split. This is a bit less than that, but that's the industry standard roughly. Okay, and let's familiarize ourselves with the data first so we actually know what we're working with here. And let's see the class names. Class names. Okay, so as you can see, we have 10 classes in our data sets, from t-shirts to ankle boots. And every one of these classes will get an index. And this index is basically there to say, okay, the t-shirt corresponds to index 0, which means the first ever neuron of the network output will be the value that's used for the t-shirt class. And to get access to the index, let's also create a new variable. And if anyone is not familiar with Python programming, it's not that, well, that complicated in this sense, because we're only building a simple model. But of course, Python is required to do more complex neural network work here. If anyone has questions, you can also ask them later after we're done with this implementation here. But if anything does not work, please feel free to put it in chat. Okay. And then we'll also output the classes here. Okay. So t-shirt corresponds to class 1, the first index, so the first neuron, and then ankle boot index 9. And this will be the same as when we say train data.targets. Targets will be of our training set. The first image will be an ankle boot image. Second one is a t-shirt. Third one also a t-shirt, and so on. So that way we know, okay, when a network predicted what the first image would be, we can compare it to our target for that index in that sense. Okay. And well, let's visualize the image shape so we know what tensor we're working with. Image and label equals, let's assign this from the first image in the list, and then print this out as well. So if anyone is familiar with, I don't want to print this out like this, not like this, sorry. So we want the shape, not the not each numeric value for every pixel here. If anyone is familiar with Python programming, normally in a program you would put print and then string of image dot shape. But in this case, Colab is configured that way that you don't need this, and it works if you only separate variable names by comma. That will also print them out. Okay, so our first image in the training set is of size 1, which is the color channel. So we have only one channel because it's grayscaled. And then width 28, height of 28, and the label is 9. So it's an ankle boot. But I don't think that's, well, visual enough yet. So let's visualize the data a bit. And that's, yeah, okay. Put into the data this. And for visualizations, we'll use a library called matplotlib. That's commonly used in machine learning tasks. And this allows you to visualize images or tensors in different formats. In our case, we need an image visualization. So first, let's get the image and label here. Train data of 0. And since we want to visualize an image, in Matplotlib, this is how you do it. plt.image show. And then we need our image. .squeeze will squeeze any white space. That's optional in this case, but I always like to do it so you don't have any gaps in your images. And then a color map, in our case, because it's grayscaled, let's use a grayscaled color map. The title of our visualization will be the class names of label. So the label here is the index, essentially. And if we put the class name, which is a list of this index, index 9, will be the name ankle boot. Okay. We don't need an access, and then it visualizes. So this is how this image would look. Okay. I have an ankle boot image, 28 by 28 pixels. Everything is grayscaled. Nice. Maybe we want to visualize a bit more images, because that's the central part of machine learning. You first have to get really familiar with your data and have a really good understanding of what you're working with, so you can create good neural networks with that. What I'm doing here is I'm creating a manual seed, and the seed flavors the randomness. So when we're selecting images at random now, the randomness is deterministic. So we're selecting random images, but if we're putting the same seed, it will always be the same random images. So if we're putting a seed of another number, for example, 50, would be different images we're selecting. This is essentially flavoring the randomness, if that makes sense. Okay, let's create a figure to visualize this. plt.figure. 4 images in every row, 4 images in every column, so 16 total. And then we need to iterate over our data set to visualize them. For I in range, so for every image between 1 and our rows times columns plus 1, because it starts at 0. We're gonna extract the random index. And I'm saying random here, but it's not actually random. So in PyFMAT and PyTorch, the random index is, well, It's deterministic if you set a seed. It's only random if this is random as well. Rand int is we need a random integer number between 0 and the length of the training data. And then it should be one integer. Don't worry about the dot item for now. That's essentially used because we want to return a tuple, but if any of you are not computer science people, just don't worry about this. We just need this to work properly. Okay. And then let's extract an image of our random generated index. And now put it into the figure. Okay. Now we have 16 images visualized. This is how it would look. And if we would input this image into our new network, we would want to receive a ankle boot label as output. But to work with this data more efficiently, a data set is not that effective, mainly because just think about if we would load all of these 60,000 images into memory, that would cause a lot of well, a lot of RAM to be used. And since we don't want that much RAM to be used, but also not load them one at a time because that's very slow, we're going to create a data loader, so a specific class that's just there to create an iterable of our data set that is there to, well, work more efficiently with our machine learning projects. So let's start section 2 with creating the data loaders. And again, we're going to use the PyTorch libraries here, since they already have a predefined class for that, which means that we can use that very quickly. Let's name them train loader. And first, we're going to define a batch size. So how many images we want to load into our memory at once. In this case, let's go with 32. Then create the data loader with the parameters of having first data loader for the training data with a batch size of, or defined batch size. And we want to shuffle the data. So it will always be randomly select images. That won't be true for the test data set or the test loader, which we'll also create here. Test data and shuffle is false. Okay. So now if we print train loader and test loader, we can get our classes here. Nice. Okay, let's visualize them also a bit more. So let's see how many batches we have in total in the test loader and also in the train loader. So roughly 2,000 batches in the test loader and the train loader. 2,000 times 32 images, so we should be roughly at our 60,000 that yeah, we have in our data set. And if we now output the shape, let's first get a train batch. And the train batch labels. And we do this by getting the next iteration of our training data loader. So this will give us the next batch of images. And let's visualize the shape and the label shape. Okay. So now we don't have a shape of 1 times 28 times 28 anymore, but 32. So 32 images times 1 color channel, 28 width, 28 height, and then 32 numbers, which are the labels in this case. Okay. We could visualize one lastly and then move on to the actual model we want to create. So let's visualize what we're gonna get from our data loader. Again, with a manual seed of 42. And that's a commonly used random seed number simply because it's from the Hitchhiker's Guide to the Galaxy, an answer to everything. And again, get a random index. In this case, we want to get a random index of our batch. So length of the train batch. And of size 1 again. Again, dot item. And get the images, image and label here. Okay. Nice. Now if we visualize this, we can see we have the same image that we got in our training set here. But in this case, it's loaded from the data loader, which means it's more efficient and better to work with than with the data set itself. Okay, now we can actually move on to the interesting part, to the actual model itself. So part 3, the neural network. And just like I said, we're going to build a simple neural network, not that complex. And since we're doing that, we need to have for every input neuron, so you might remember here, a numeric value to input. So we're going to pick every pixel value and create an input neuron for this. And now our images are in these matrix tensor formats, and we need to flatten them. So PyTorch has a flatten layer for this, which takes the image of size 28 times 28 and will flatten this out into size, well, 784. So 28 times 28 in a list, essentially. And again, we're going to use a PyTorch class to create our, let's call this fashion model. And it will inherit from torch.nn.module. And we need to for torch and then as well. Okay. Then we need to define our model, so how it's actually built. A lot of more complex mathematical work is handled by PyTorch, and that's great for this session because otherwise we would have to implement it ourselves, which would have taken ages. But in this case, we need for our neural network, it is generally built in, well, 3 different neuron layers. You always have an input layer and an output layer, and then a specific number of hidden layers. In our case, we'll use 1 hidden layer, and the input layer has 784 input neurons. So for every pixel of the image, 1 neuron. The output layer has 10 neurons in our case, for every class 1 neuron. And for the hidden layer, we'll need to specify a specific number of neurons that we want. So for example, 16 would be my choice in this case. But first, we're going to put them as parameters in our class here. And now let's define how the neural network is built. So we'll create in this case, PyTorch lets us create a layer stack, which means we have dense connected layers like this. And in our layers, we use a sequential neuron layers. First, a flatten layer to flatten out the image into our format that we want. Second, a linear layer. So this linear layer will take the flattened numbers as input and output the output the hidden units in this case. So how many hidden neurons we have. For example, here we'll have 784 input neurons, outputting 16 hidden units for 16 hidden neurons in the hidden layers. So the hidden layers are the ones between the input and output layer. Here we have 2 in our case. Here we'll only build with 1 hidden layer. All right. Then for the second, let's also create another linear. Another linear neuron layer, again with the same format as before, but we're going to use the hidden units as input shape and the output shape as output units. Okay. Normally, you can also put functions in between to get nonlinearity and other specific things, but we'll keep it simple for now. So this will stay like this. And now we need to define a forward pass function. So what the neural network actually does when it receives an image. This will take itself and the input as an input parameter and return the output of this layer stack that we defined here when it receives this input. Okay. Now our class is created, but we still need to define our network. Let's do with a manual feed of 42 so it's more predictable. And we'll create a Gaussian model. In our case, the input shape, like this, input shape will be 28 times 28. The hidden units, let's say we have 16 of those. And from the output shape will be the length of the classes, so 10. And then print the model out so we can see what it looks like. Okay, this is how our simple neural network looks like now. Normally, as I said, you would want to build a convolutional neural network for this kind of task. And then you would add convolutional layers here for the flattened layer. So you can have more spatial understanding of how the image is actually composed. But for such a simple task with like not very complex images, we should be able to get to a decent accuracy also with this architecture. Okay. Now we have our model defined. Let's test it with some dummy input. So dummy x equals, let's create a random tensor with PyTorch of size 1, 1, and 28 and 28. Resemble as well. And it has to resemble that because we need 28 times 28 input features, otherwise this neuron layer wouldn't work, right? Because we have 784 input neurons. So the shapes always have to match. And that's output what our model predicts for this dummy neuron. Okay, so now we can see our output from our neural network, which is for every output neuron a numeric value. Now it's random because it's not trained yet. So this is just a random tensor, and as of now, the highest number, which is this probably, would mean that this class would be predicted as the most likely label, but we want it to work. So the next part is training it on the data we have downloaded before to make accurate predictions here. Part 4, training. And this is most likely one of the most important parts of this. And since the optimization process is essentially what gives the neural network the ability to learn and, well, be effective. And yeah, so I'm naming this criterion. You could also name this loss function. They are the same thing, but just different descriptions of it. And for classification problems, want a loss function of cross entropy loss. Other common loss functions would be, for example, mean squared error. That would be for the linear regression, for example. So you would take the difference between the actual value, the predicted value, square that difference, and that would be your error. But in this case, for classification, we'll use the cross entropy loss algorithm, loss function. And then for an optimizer, stochastic gradient descent, SGD. Again, everything from PyTorch, because the mathematical implementations are quite complex, but here we are not worried about them for now. And a learning rate of 0.1. Okay. Stochastic gradient descent is the algorithm that would take the steps of updating our parameters, which we defined here. So the parameters we update are the model parameters. And we do that with a learning rate of 0.1. That's the size of a step you take. So a large learning rate would mean you would take large steps, and a small learning rate would mean you would take small steps. Generally, it's best practice to start with a larger number and then gradually decrease it when you converge more toward your minimum. So we'll start with 0.1 because we don't implement a scheduler here to keep it simple. But normally you would also change this during the training process adaptively. Okay, let's train this now. TQDM is a library to have progress bars, but probably I'm not going to use this now because we're running short on time. Create a manual sequence of 42. Again, specify the number of epochs, which are the runs through the training set we're going to take to train a model. So 3 epochs means we're going to go through the training set 3 times and train the model 3 times. Yeah. So for every epoch in range epochs, which means we're iterating over them. And let's output this nicely. Maybe like this. Epoch. Okay, you can see the epoch number. Okay. So now for every epoch, we're gonna go through a training process. The first thing we do, set the training loss to 0. And now for every batch and input and label, input X and label Y in our enumerate, which means we're iterating again, in our train loader, we will first set the model to training mode, predict the output of the model from the input image X, then compute the loss with our criterion or loss function we specified earlier. So the error between our prediction and the actual output. And then add this loss to our train loss. Another step that I didn't mention in the theory part is the resetting of a gradient so they don't accumulate, and otherwise the gradients, which means the derivations of the loss function you would calculate to know where you would step down, would always accumulate. That would lead to unstable training. So you reset them in every batch training process to start from 0 again. So 0 the gradients, and now perform backpropagation. That's an algorithm used to calculate which neurons are responsible, or which parameters are responsible for the errors. And then once we know which are responsible, we'll take a step with our optimizer in the direction to minimize our loss. That's the most important part. This is the training process of a neural network. So if you remember anything from this coding session, it should be this cell here. Okay. And then lastly, let's print out some information so we know the training process works. If a batch is divisible by 400, so every 400th batch, we want to print out the number of batch we're at. Out of the total numbers of batches we have here. And print out train loss. Oh wait, not here, not here. Maybe it's better if we do it here. Train loss. Okay, this should work for now. This should train our model. Wait, criterion is not it. Oh yeah, forgot to run this cell first. And now our model is training, so we're iterating very fast. That's because the images are very small, so we can compute it, well, 60,000 images in basically no time. Now that the model is training, let's first maybe get test it on the test set once, so we know it actually works very well. NumPy matrix lib. test. And then we don't want to train our model when we test, of course, so inference mode. Test loss equals 0. And then just to double check, this is optional, but I like to put the model into eval mode as well. Normally you don't need this when you have inference mode already enabled, but best practice. And then the same as in the training process, we're going to iterate through our samples in the loader, make a prediction, and then calculate the loss, and then output this afterwards. So in the end, let's output the test loss so we know how good we are. And ideally, this should be small. Okay, so it's 0.51. That's acceptable. Okay, for this kind of network, that's a good loss. That means it learned rather effectively. Normally, you also input your loss here and then have a nice loss function, so you can visualize how your model learns over time. But for the simplicity's sake, we're not going to do this, and also because we only have a couple minutes left. And lastly, for the last part, we'll just visualize a prediction our model made. Because now it's just number. It means, okay, loss of 0.5, but what does it actually mean? Is the model actually effective? So with partial inference mode again. We'll get the first test image. Make a prediction on this test image. And then get the prediction for this image, which is the maximum, so argmax. Wait, cred.argmax, sorry. Of, oh, we need one dimension. And item because it's tuple. Okay. Now that's a prediction. Let's visualize this again in the last matplotlib visualization. X.squeeze. Again with gray. Yeah, okay. And we're gonna do this like this. So, as you can see, the model predicted this accurately. Ankle boot and ankle boot. If you would change this to the first image, also correct. Second trouser. Shirt. So this seems to work rather effectively. The model predicts almost always what's actually in the image depicted. I know this probably was a bit much for the first ever coding session of neural networks, but I still wanted to make like an interesting project so everyone has fun doing it as well. If anything is unclear, please feel free to ask questions. And we don't have that much time left, but yeah. So let's see. Some are in the chat. Yes, exactly. Google Colab is very beginner friendly. You could also do it yourself on your command line or on your own code editor, but that's, well, you need to set that up first, and that takes a lot of time. So you also don't have access to Google's server. Right, any questions? I will also share this notebook that we created just now in the Use STEM initiative group chat, so everyone has access to it and can take a look at it themselves if they couldn't participate in building along. Okay, thank you, Sven. Yes, yes, it was a pleasure. It was a pleasure to present everything to you. So hopefully, it worked all well for you.
Okay, I think if we are done with the session, we can go ahead and conclude it. Thank you so much, Mark, for being a part of STEM Quest 4.0. I'm pretty sure everyone really enjoyed this session. If you guys have any other questions for Mark, you guys can text me on WhatsApp and I'll make sure they reach him. And